Hi Bobcats! In this video we're going to introduce ice charts. Ice charts are a very powerful problem-solving tool for solving equilibrium problems. It's really just a way of tracking the stoichiometry of the reaction as we move from an initial set of conditions to our equilibrium conditions. And remember, this is a type of problem that we're going to be doing throughout the end of the semester. So it's really important to get a good grip on how we work with ice charts. Our objective for this video is to use ice tables to solve these equilibrium problems. Ice charts are a way of keeping track of our stoichiometry as we move from the initial conditions to our equilibrium conditions. We're going to start by writing the balanced chemical reaction. That's going to be the top line of our ice chart. Because that top line is the reaction, sometimes people refer to these as rice charts, but more often you're going to hear ice charts. The next line will have the initial conditions. So the problem will read something along the lines of so many moles of this chemical and so many moles of this other chemical are introduced to a 3-liter flask. So that gives us the data for our initial line. And then you have to figure out, is this reaction going to go in the forward direction, or is this reaction going to go in the reverse direction to reach equilibrium? Now, in some cases, like the example that's in this ice table at the bottom of this page, there's only one direction that it could possibly go. There is no ammonia present for our initial conditions, so the reaction can't possibly go in the reverse direction. It could only go in the forward direction. So when we hit the C line, which stands for changes in the concentrations, we are going to lose some of our reactants and we are going to gain some of our products. So the changes for the reactants in this case will be negative and the changes for the products will be positive. So that will happen anytime the reaction is going in the forward direction. In order to reach the E line, well, E stands for equilibrium. If we know where we start, our initial line, and we know how it changes, we can get our equilibrium line by adding together the initial line plus the change line. So let's look a little bit more closely at this ice table. If we're starting with 0.1 molar hydrogen and 0.1 molar nitrogen and none of the ammonia, the reaction will have to go in the forward direction to make ammonia. Since no ammonia is present, we can't go in the reverse direction and make hydrogen and nitrogen. So we know that we're going to lose some hydrogen and we're going to lose some nitrogen. Well, every time we lose 1 mole of nitrogen, we're going to lose 3 moles of hydrogen. That's just simply the stoichiometry from the coefficients in the balanced equation. Since there's no coefficient in front of nitrogen, that's understood to be a 1. So as we lose reactants, we need to keep that 3-to-1 ratio, minus 3x for hydrogen and minus x for nitrogen. We're using x because we don't really know yet how much stuff we're going to lose to reach equilibrium. And so then finally, to write up our equilibrium line, we're going to take our initial line, which for hydrogen is 0.1, and add to it our change line, which is a minus 3x. So at equilibrium for hydrogen, we have 0.1 minus 3x. We'd follow that exact same procedure to get the equilibrium line for nitrogen and for ammonia. So that's where we get the 0.1, which is what we started with for nitrogen, and then minus x for its change. So at equilibrium, we have 0.1 minus x. And then for ammonia, since we started with 0 ammonia, the change is going to be a plus 2x because we're going to make ammonia, and ammonia has that coefficient of 2. And so then at equilibrium, we have 0 plus 2x, or just simply 2x. To summarize how to make an ice chart, start by writing your balanced chemical equation, label the 3 lines underneath it, I, C, and E for initial change in equilibrium, and then fill in what you're given. Often for the change line, it's obvious to see which direction it's going to go, but sometimes it's not, and so you'll need to calculate Q anytime it's not obvious. So whatever sign or whatever side of the equation is increasing, you'll want to use the positive sign on the change line. Whatever side is decreasing, you want to use the negative sign. And then don't forget to multiply by the coefficient. And then for the equilibrium line, just make sure you take your initial line plus your change line. In this example, we have sulfur trioxide in equilibrium with sulfur dioxide and oxygen. Initially, we have a partial pressure of SO3 of a half atmosphere, and it doesn't mention any other chemicals, so that's the only thing in there to begin with. By the time we've reached equilibrium, the partial pressure of SO3 has dropped to 0.2 atmospheres. From this data, we need to calculate a number for Kp. So I'm going to rewrite our reaction, which is 2SO3 in equilibrium with 2SO2 plus O2. Now, all of these chemical species are gases, so they will all play into our Kp expression. Initially, the only chemical we have is SO3 at a value of a half atmosphere. So that means we don't have any SO2 and we don't have any O2. So the reaction can only go in the forward direction. By going in the forward direction, we're going to lose some of our reactant, so it's going to have a minus sign, and it has a coefficient of 2, so we'll take a minus 2x. We're going in the forward direction means we're going to make SO2, so it'll be a positive sign because we're making it, and we have a coefficient of 2 that we have to multiply by the x. And for oxygen, we'll be making it as well, and that will be just plus x because it has a coefficient of 1. At equilibrium, we'll have 0.5 minus 2x for SO3, we'll have 2x for SO2, and we'll have x for O2. But we have a little bit more information as well. We were told that at equilibrium, the SO3 partial pressure is 0.2 atmospheres. So we know that this piece right here that I'm drawing the box around has to be equal to 0.2 atmospheres. 0.5 minus 2x has to be equal to 0.2. So let's see, if I move the constants over to the right-hand side, this will change into minus 2x is equal to minus 0.3. If I divide both sides by minus 2, I get that x is equal to 0.15. So if I'm going to calculate a value for K, I can only use numbers that are at equilibrium. We know that SO3 at equilibrium is equal to 0.2. Right, so this 0.5 minus 2x on our equilibrium line, that is going to be equal to 0.2. Our value of O2 at equilibrium is equal to x, which is 0.15, and our value of SO2 at equilibrium is 2x, so that'll be 0.3, because 2 times 0.15 gives us 0.3. Our K expression is going to be SO2 squared, since it has a coefficient of 2, times O2, and all divided by SO3 squared. So if I plug numbers in for this, for SO2, we're going to plug in 0.3. This is taking our values off the equilibrium line. For O2, I'm going to plug in 0.15. And for SO3, I'm going to plug in 0.2. And that one also has to be squared. So now I'll run that through my calculator. And we have 0.3 squared times 0.15 divided by 0.2 squared. And so that gives us a K value of 0.3375. The numbers that we were given throughout the problem all have 3 sig figs, so I should probably round that to 0.338. There is our final value for Kp. In this problem, we have an equilibrium reaction with hydrogen and iodine in equilibrium with 2HI. We're given that the K value is 50.5, and we're given initial numbers of moles that are added to a 2-liter flask. I'm going to set up the ice chart up top. So we're going to have hydrogen plus iodine in equilibrium with 2HI. All of these are in the gas phase, so they will all go into our equilibrium constant expression. We can't use the numbers given straight off because they are moles and we need to have molarity into our K expression. So we're going to have to divide through by the volume of the flask. So 1 mole divided by a 2-liter flask gives us 1/2 or a half mole per liter. And that's for the hydrogen. Ditto for the iodine. It's 1 mole in a 2-liter flask, or 0.5 moles per liter. And initially it doesn't say anything about the HI, so we don't have any of it present. This reaction has to go in the forward direction to reach equilibrium, so our change for hydrogen will be minus X, and our change for iodine will be minus X, and our change for HI will be plus 2X. So at equilibrium, we'll have 0.5 minus X, 0.5 minus X, and 2X. The equilibrium constant expression for this reaction is going to be HI, quantity squared, divided by H2, and divided by I2. Now I can plug the equilibrium values in here and solve for X. For K, we have a value of 50.5. At equilibrium for HI, I've got 2X, and that will be squared. And in the denominator for hydrogen, I have 0.5 minus X. And for iodine, I have 0.5 minus X as well. So that becomes 0.5 minus X times 0.5 minus X, or 0.5 minus X quantity squared. This is looking a little hairy because it's going to be a quadratic equation involving x squared terms, x terms, and constants. But there's a trick. If you look closely at the equation that I just wrote, the right-hand side is a perfect square. It's squared in the top and it's squared in the bottom. So the next step I need to take here is to take the square root of both sides. So I will take the square root of that right-hand side, and I'll take the square root of that left-hand side. Over there on the left-hand side, if I take the square root of 50.5, I'm getting 7.11. If I take the square root of the right-hand side, I get 2x over 0.5 minus x. Now the algebra here gets a little tedious. I'm going to multiply both sides of this equation by 0.5 minus x. That's going to give me 7.11 times 0.5 minus x is equal to 2x. If I distribute that, the 7.11 times 0.5 gives me 3.56, and then minus 7.11x is equal to 2x. If I add 7.11x to both sides, let's see, that'll be 3.56 is equal to 9.11x. And then if I divide both sides by 9.11, I'm going to end up with 0.39 is equal to x. Okay, so we were not asked to find x. We were asked to find the equilibrium concentrations. So we're going to have to take x and plug it in to our equilibrium line. For HI, we needed 2 times x. So if we take 2 times x, our equilibrium concentration of HI will be 0.78. And then for both hydrogen and iodine, we had 0.5 minus x. So 0.5 minus 0.39 gives us 0.11. So both of these guys are equal to 0.11 at equilibrium.